Hi everybody, welcome back. It is April 20th and we are going to continue on our journey in learning about organic chemistry. You will need Table R out today and we're going to start talking about the class of organic compounds known as halocarbons. Okay, so a little bit of background information on halocarbons. They're actually really important and pretty fascinating as a group of compounds. Most of them are human-made gases. They can also be known as halides, and they have good and bad to them. I would say the bad outweighs the good though. So I've blown up part of Table R here. It's the first class of compound listed, functional groups listed here, the 4 halogens. We'll talk about the general formula and this condensed formula and naming. I always like to look at Table R as kind of like a cheat sheet in a way. It's a great resource to have so that you can, if you can interpret what's going on here, you should be able to name or identify organic compounds that would belong to whichever class of compound is listed here. In this case, we're focusing on halides. A little bit more about this general formula column here. At the bottom of this table, it tells you in fine print that R represents a bonded group of atoms. So this is a variable group. This could be 1 carbon, 2 carbons, 3 carbons, 4 carbons with hydrogens coming off of those carbons. It will vary. What the functional group, though, is for this particular class would be represented by X here. It is one of the halogens, fluoro, chloro, bromo, or iodo. Condensed formula is very useful in organic chemistry because we're starting to get into larger compounds. So there's quite a few atoms involved here. And this kind of separates out the different regions of this molecule, and it allows us to see it in a better way and giving us more information, let's put it that way. But if I were to write the structural formula, I have CH3 here. Okay, then next to that C is a carbon. I'm going to put the hydrogen though up on top. Could I have put it down here? Absolutely, it really does not matter. I'm then going to put the chlorine at the bottom, and then I have another CH3. So here is the condensed formula. This is the structural formula, okay? And we could write this as a molecular formula. That is C3H6,7H7Cl, molecular formula. Let's look at the name of this. You're told here it's called 2-chloropropane. Let's break that down a little bit here. We've got propane, the parent carbon backbone. 1, 2, 3 carbons. We have a propane. It ends in ane because there's single bonds between those carbons. We have the number 2 and chloro. 1, 2. The second carbon has a chlorine bonded to it. So therefore we are going to call this 2-chloropropane. Let's look at a few other examples. The first one I will deal with is CH3, 3 hydrogens, the carbon, and here's a bromine. Now, if I want to draw that out, CH3Br. Again, it does not matter. I could have put the Br in any of the other positions, but this is the structural formula for that molecular formula there. Now we have CCl4, a carbon with all chlorines attached to it. I could draw that out as such. And if you recall, by the way, from a few lessons ago, these are tetrahedral shaped compounds. These belong to what we call chlorofluorocarbons, and you may have heard of these in the past. CFCs is the abbreviation for chlorofluorocarbons, and CFCs are notorious for, what is it? For destroying the stratospheric ozone layer. So I mentioned earlier in this mini lesson that there's good and bad. The really bad thing about these human-made gases are that they are destroying that stratospheric ozone layer, and they are persistent. That means that these compounds stay and persist in the atmosphere for 100 or more years. So they're doing damage to the ozone layer for many, many years. So, what's the good with them? Why did humans make these? Well, the good uses of these halocarbons were that they were used as refrigerants. They were used in certain fire extinguishers. They were used as propellants in aerosol spray cans. So they had a lot of really good uses. But once it was discovered that they were destroying the stratospheric ozone in 1987, the Montreal Protocol was an international treaty that was passed with a focus on phasing out the use of halocarbons in these products, so that we could protect the ozone layer. The ozone layer is really important because it protects humans and animals and plants from harmful UV rays, and it helps in crop productivity. Okay, let's look at another example here of a halocarbon. I didn't draw in all the hydrogens here, but as a reminder, if they're not drawn in, you do assume that they exist there. And we could just take a quick look at naming this example. Let's look at the parent backbone. So just like this example had 3 carbons, it's a propane. This one has 1, 2, 3, 4, 5, 6 carbons. It is a hexane. And you will see it is definitely a halocarbon because there's chlorine involved in it. Well, now there's 2 chlorines. If we number, just like we've had in the past, we would number the carbons, and we would note that 1 chlorine's on the second and 1 is on the fourth. So it's 2, 4 dash dichlorohexane. Now, I want to move on and talk about what we call organic reactions. These are chemical reactions that create organic compounds. So I'm going to introduce 2 of them today. The first organic reaction that you need to be familiar with is known as a substitution reaction. And just like if I were absent from class, a substitute would come in and replace me. In a substitute reaction, a hydrogen in this compound is being replaced by a halogen to make a halocarbon. So you could see it written this way. I'm going to actually draw out the structural formulas, which again has its benefits of perhaps making it easier to comprehend. Running out of room there, but we got this. Okay. So I did that kind of quickly, but CH4, methane, reacts with chlorine gas, diatomic chlorine, to yield carbon with 3 hydrogens and a chlorine. This is our halocarbon. In fact, this is going to be called chloromethane, and that's hydrochloric acid. So this is considered a substitution reaction because one of these hydrogens is taken out and substituted with a chlorine. The other chlorine bonds with that hydrogen that was removed to make hydrochloric acid in this case. Okay, we're now going to look at another example of organic reactions known as addition reactions, in which we can make a halide or halocarbon by adding the halogens to a double or triply bonded carbon compound. And as a reminder, whenever there's double or triple bonds associated with carbon compounds, they're considered unsaturated. They have less than the maximum number of hydrogen atoms. I'm also going to show it as a structural formula, or a series of structural formulas, right? So here we have, by the way, ethene, 2 carbons, 4 hydrogens. It has to have that double bond there in order to have the octet achieved. Ethene reacts with bromine gas to yield this compound. Well, I'm going to write it down here for more room. I still have my 2 carbons. I still have my 4 hydrogens. But I've added, in an addition reaction, 2 bromines. So addition reactions require that there's a double or triple bond in a carbon-based reactant so that we can add in the bromine. We have our octet achieved here, but that double bond has changed to a single bond there. Let's name this. We look at the parent. It is ethane. 2 carbon backbone. We have 2 bromines, and we need to indicate where they are. So this is 1, 2 dash dibromoethane. Thanks for watching. Bye.